Chapter 5, Network Cabling, Part 1. So in our lectures this week, we're back down here at the bottom of our TCP/IP model. We're back down here at the hardware layer. But whereas last week we were looking at layer 1 in a very broad sense, like how do we cable things and what do our data centers look like, this week we're looking at a very specific area of our layer 1, and that's cabled networks, right? It's not as common as it used to be. Since in the rise of wireless and wireless access points and wireless routers and all that, for home use, we're seeing less and less cabled networks. I mean, you might see your wireless router connected to your cable modem by a coaxial cable or something like that. But for our nodes, I mean, we don't really wire in our iPads and iPhones, all that kind of stuff. So where do we see this still? Predominantly in enterprise, right? In cubicle land, in most work centers, all your PCs, your end user devices have a network cable attaching them to some switch somewhere. In our data centers, our servers are almost exclusively all cabled up. And it turns out there's all kinds of different cables, all kinds of different connectors, and all kinds of different scenarios when we would use different ones. So why so many choices? Because our transmission techniques today are really, really varied. It's kind of hard to draw parallels between copper cabling and fiber optics, right? But all of them define data transmission in a cabled environment. So let's get some terminology out of the way. Let's start by discussing what an analog signal is. Now, an analog signal is really just this. This can be represented as varying voltage, a varying electrical signal. This could be described as a sound wave, right? It could be described as a seismic wave moving through the earth. Analog signals are continuous. See, this is one continuous line right here. And it makes a wave. And it's repeatable. Notice this. This could be the electrical signal coming out of your wall for alternating current, right? This could be current variations, whatever. They all have the same waveform structure to them. And it's called a waveform because it looks like a wave. And if you measure from peak to valley over here, right? Notice this low point versus the high point. That's called the amplitude, and that's the height of your wave. I can also measure wavelength. Let's say from peak to peak, right here. Right? So my signal can be characterized by my amplitude and my wavelength. Now, even though we use analog signaling for a lot of things, they do have some drawbacks. For one, this is just, well, in this case, slowly changing voltage. Well, it's got to be imprecise to a certain degree. It's also going to be susceptible to transmission flaws. A great metaphor for this is a vinyl record, right? You put that in a record player, put a needle on it, and what does that sound? That's just basically a waveform melted into the record that a needle traveling along measures differently. Well, gee, why did CDs get so popular back in the 80s? Records got scratched. I mean, CDs get scratched too, but a scratch across a phonograph record would alter this waveform. Likewise, a piece of dust on there or something else. And again, this big thing is it's susceptible to transmission flaws. Let's compare that with digital signaling. Remember what digital is, right? It's an on or off state. And while this can also be measured in a waveform, it's binary. It can only be one of two states, 1 or 0, on or off, and that's it. So it's very precise. Absolutely. And this is where our binary numbering system comes from. We represent these things as numbers because as humans we can think that way, but in reality we're looking at the presence or the absence of voltage. Now, it doesn't mean I can't use my digital signaling to reproduce an analog signal. That's exactly what CDs do. But I'm doing it more in this little staircase style right here, right? And if I do this enough, I can reproduce an analog line. But one big difference, it's not continuous. It's just little sample points along the way, right? If I get enough of them, I can get a very high granularity line, but it's still not continuous. Our modern data transmission relies on digital transmission. That's the whole point behind it. So how do I go back and forth between them? Remember these days of when you have to have dial-up connections? Well, if you don't, I certainly did. You would take your telephone line, attach it into a device called a modem, which actually stands for a modulator-demodulator, and all that thing did is convert between the analog signal of your phone line, because that's all a signal on a phone line is, and convert it into the digital transmission that a computer understands. And that's exactly what we mean by data modulation, hence the term modulator-demodulator. It's also a good chance to point out how that term gets misused a lot. Our cable company all the time, if you're talking to them, especially their tech support, and they'll ask you to reset your cable modem, quote unquote. Well, it's not a cable modem. That's an all-digital signal. A cable modem is really a router. But a DSL modem, digital subscriber line, which talks across phone lines, yes, that is still a modulator-demodulator. Other terms we see thrown around quite a bit. We have this thing called baseband and broadband. And a lot of times, baseband or broadband is used synonymously with the term high speed, meaning our cable, internet, and DSL, and that kind of stuff. There is a difference, though. In pure definition, a baseband transmission is traveling using only one kind of signal across a wire. That's just it. For example, a Cat5 network cable that's just transmitting data. What about a broadband? Right? Well, we totally have that cable, quote-unquote, modem we talked about. That's a broadband transmission. Because what's coming in from our wall? It's a piece of coaxial cable, right? And traveling along that coaxial cable is our TV signal, very likely our phone signal, although that is over IP nowadays, and our cable internet, which is digital data. So we have multiple kinds of transmissions sharing a single wire. That's where terms multiplexing comes in, right? How do we get those different forms of data, of transmission onto a single wire? Well, I do it with a device called a multiplexer, right? And what that does, it takes many separate channels and combines them all into one and blasts them across a wire, right? At the other end, though, I need to have what's called a demultiplexer. That splits them back out again in their separate components. It looks kind of like this. And there's different kinds of multiplexing going on. What we're looking at here is called time division multiplexing. So where really, if I get three separate transmissions over here off to the left, transmission A, B, and C, and these are three separate channels altogether, three separate signals, my multiplexer just plugs them in. And it actually does it in a time-sharing method. Right, see what's happening here? It sends some A, some B, some C, some A, some B, some C's, and launches them across. So I've got all three transmissions going across my wire at one time. At the far end, there's my demultiplexer, right? My demux, breaking them back out into their component signals. Other terms that they get misused pretty badly: throughput and bandwidth. Throughput. And they're both usually expressed in terms of speed, kilobits per second, megabits per second, whatnot. Strictly speaking, though, throughput is what defines the amount of data transmitted during any period, right? That's our 56 kilobits per second, our 50 megabits per second, whatever. I know my Time Warner connection I have at home is 50 megabits coming down. In a lot of advertising brochures and stuff like that, you'll see it termed, the bandwidth of 50 megabits. Well, it's not bandwidth, it's the throughput of 50 megabits. Strictly speaking, if we're doing Merriam-Webster here, bandwidth is defined as the difference between the highest and lowest frequencies that particular medium, that particular type of cable can transmit. It's really a technical difference. we're commonly going to see them both expressed as a bit rate, kilobits, megabits, whatever. But if we want to be strict about it, that's a measure of throughput. Here's our different measures right here, right? And it wasn't that long ago when we were measuring kilobits per second. Notice how the letters are. kbps. The B is small, right? That means kilobit. A capital B right there, it means kilobyte. 8 bits to a byte, a separate measurement altogether. When we're speaking throughput, we're speaking kilobits per second. Well, right now for internet service and home use, we're in the megabit range, although internally on our networks, gigabit is pretty common nowadays, with 10 gigabit up and coming. At some point in the future, we're going to see terabits per second, right? That should stream that video across pretty fast. All right, let's take a look at one of our most common cables we see in most wired network environments, and that's twisted pair. And this can be any of the twisted pair cables we've been using for over 20, 25 years now, right? These are our category 3 cables, category 5, Cat 5e, Cat 6, and now Cat 7. What it is a piece of cable, I don't know, maybe about a quarter of an inch in diameter, maybe a little less. Has some type of rubbery plastic insulation on the outside, and is usually some color. It could be gray, yellow, red, whatever. If you cut it open, you're going to see 4 pairs of smaller wires inside of it, right? Each one of the pairs are color-coded. Notice that one will be solid and one will be striped. Solid, striped, solid, striped, solid, striped. And they have a twist going on to them. They're twisted. Well, why twist them? What's the point behind that? It's this thing called crosstalk. The signal going down a piece of copper is an electrical signal, right? Well, when electricity bursts down a piece of copper, and that's what this is, it gives off a magnetic field around that copper. See these little waves emanating out from this black one right here? Well, those waves come in contact with the other wires that are inside the cable with it, right? When these magnetic waves hit a piece of copper, they induce a magnetic signal inside of it, or an electrical signal inside of it. That's called induction. In a lot of cases, that's how transformers work, where it's done on purpose, right? But in this case, this induction is it's causing something called crosstalk. Another word for that is EMI, electromagnetic interference. So if it's generating electrical signal on these other wires, that's going to garble the actual signal we want to have come across there. If we didn't have a way of dealing with this, category 5 cable wouldn't be possible. The twists are there to reduce that crosstalk. It has to do with the way that it interacts with each other and helps suppress those magnetic waves. But what it really comes down to, if those twists weren't there, the cable would not be able to transmit data. If you ever get to where you terminate and learn how to put tips on these cables, you have to cut the end of the cable off and straighten out the twist just a little bit to get it into the RJ45 connector. Well, you have to be really careful about how much you straighten, because if you straighten about much more than 3/4 of an inch, that cable is not going to talk. Now, there's all kinds of different twisted pair combinations, all different grades. We talked about this. Cat 3 is the old 10 megabit cable from the Ethernet standard back in the 90s, late 80s, early 90s, up in there. And over time, we've evolved to higher and higher throughputs on our cables. Commonly right now, Cat 5e, which can handle gigabit speeds or higher. This TIA-EIA standard that we talked about in a previous lecture, its most common implementation is TIA 568, and that defines how the connectors are placed on those cables. Why is twisted pair so common? What's the big deal about it? Well, especially when you compare it to what we were using years prior, like thick net and thin net and all that, it's much less expensive. right? Really, because there's a lot less copper inside there, copper cost. It actually works really well. The maximum range on one of these cables is 100 meters or 385 feet until it has to be boosted. So that's pretty good range for most LAN purposes. And it's flexible. I don't have to really worry. I don't want to kink it. I don't want to put a 90-degree angle in it, but I can twist this up pretty tight and not have to worry about it. It's fairly durable, right? I could step on it. It's not that big of a deal. Compared to other types like fiber, which we'll see in our next lecture, I don't want to step on that at all, and I have to be really careful about how I handle it. And it's fairly easy to install, although there are some caveats to that. There's two types of twisted pair. One is called shielded, right? And check it out. Here's my twisted pair. There's this out of the sheath. But the four pairs of cables in here, they're wrapped in like what looks like this little real thin aluminum foil and this little copper net that goes around it. Well, that copper net, that shielding, needs to be grounded on either side of it, right? But what this does is it keeps the entire cable from being susceptible to crosstalk. When you're laying cable, you have to be really cognizant of where you're putting it, right? I probably don't want to lay unshielded twisted pair, which is our other type of cable, right along parallel to electrical lines running in my house. Reason? Current passing through those electrical lines. That will induce crosstalk into my twisted pair cable. If I can't avoid it, if I have to send a cable in a high EMI area, I would need to use shielded twisted pair. Right? It would help reduce that. Most commonly, though, we're using unshielded twisted pair. This is just those four pairs of wires inside a little plastic sheath, and that's it. Very, very, very susceptible to crosstalk, to noise resistance. So why don't we just use shielded twisted pair everywhere and call it a day? Cost. STP is way more expensive than the unshielded stuff. It's the kind of thing you use it when you have to, but if you can get away with using the less expensive and easier to work with unshielded twisted pair, absolutely. So we have different Ethernet standards, and this is from the Ethernet protocol, right? Defines how it's going to operate across different types of cabling. So if we look at here, our old 10 base T cable, and this is regular Ethernet, the original Ethernet standard. See, this was 100 or 10 megabits, and required a Cat 3 or better unshielded twisted pair cable. Now notice the maximum distance on all these, whether it's a 10 base T, 100 base T, 1000 base T, whatever, 100 meters, 385 feet. Why is that? What's going on with that? Well, it's kind of like this. So if this is my cable, or this is my signal, and it's bolting off my cable, and there's my waveform, that copper is not a pure conductor, right? It does conduct, but it has some resistance built into it just in the nature of the material itself. It's very hard to find a true, pure superconductor. Actually, you have to get like really cold to make that happen. So what happens is, as that signal travels over the wire over distance, my amplitude gets smaller. All right? Notice how my peaks and valleys are getting shorter and shorter. And eventually, it just evens out to where I can't tell where my peaks and valleys are anymore. On a category 3 or better cable, that distance is 100 meters, 385 feet. That's why it needs to be boosted at that point. Other standards, 100 base T. That was fast Ethernet, right? Quote unquote fast. Well, it was fast 25 years ago when it came out. It could go up to 100 megabits. Needed Cat 5 cable or better. Still 100 meters on its distance. And then what we're more used to nowadays, 1000 base T, gigabit speeds, right? So 1000 megabits per second or 1 gigabit per second. Cat 5 or better. And again, our same distance. And notice how it changes. The name of it changes a bit. The base TX when we go to Cat 6, or we get to 10 gig. base T. Right here. So what's these letters at? What there's a code to this. What does the 10 base T, 1000 base T actually mean? It's not there by accident. The 10 refers to the maximum transmission speed. So in this case, 10 megabits. The base refers to baseband. I'm not sending a different kind of signal across this wire. I'm just sending my data signal. So it's a baseband transmission, not a broadband transmission. 10 base. Then the T, the dash T, is what type of cable is it? Well, in this case, it's dash T twisted pair. Hence, we get our standard names here. 10 base T, 100 base T, 1000 base T, and so on. Well, there's a certain way that we put connectors on the end of these things. And Ethernet cables, Cat5 cables, require what's known as an RJ45 plug. Right? It looks like a phone plug. Right? That's actually called an RJ11 plug. And it's very similar, except that a phone plug only has a spot for 4 wires. Well, Ethernet cables, Cat5 and better cables, they have 8 wires, 4 pairs. 4 times 2 is 8, right? So there's 8 little slots in there for the wires to go. Is there a way I'm supposed to wire this up? Does it matter? Yes. Right? There's our TIA, EIA standards again. They define 2 types of it, standard 568A or B. And here they are. And it just defines, as you put the connector on there, which wires go into which pinout. Right? Notice on my 568A standard, starting from pin number 1, green with white stripe. Then I have the green cable. Then the orange with white stripe. And then the blue with white stripe, and so forth. It has to be in that order. On the other end of the cable, I have to cable it the exact same way. Alternatively, I could use the 568B standard. Same idea, but it swaps some of these cables around a little bit. Right? Actually, what it's doing, it's swapping my send and receive cables. If I want to make a patch cable, a straight-through cable, I can use either one of these techniques, and it makes no difference whatsoever. Guess what happens if I use 568A on one side, 568B on the other? Guesses? Guesses? Bueller? A crossover cable. Right? You've seen those before. Crossover cables are used when you wire 2 identical pieces of hardware together. Back in the day, that's how we first wired our PCs together for quote-unquote LAN parties. You'd have 2 people, somebody would drag your PC over. There was no switchers or hubs or anything like that. Each one had a NIC in the back of it, and we'd connect the 2 machines directly together. Well, I'd have to use a crossover cable, so the send and receive would be switched on either end. There's also something called a rollover cable, right? And it's not a well-trained dog. What this means is all the pins are flipped on the other end. So if I've got this order on one end, green, white, green, orange, white, so on this end, it would be the exact opposite. It would start with whatever that color is, I think it's supposed to be brown stripe, whatever. It's just flipped. Those tend to be more specialized. We see those especially with Cisco devices. Right? Cisco switches and routers have what's called a console port built into them. And it's meant for you to connect using a null modem or something like that directly into a terminal emulator so you can configure the device when it first comes out of the box, when there's no IP address on it. Pretty much it's the only time you're going to see those. What if I have to go from one type of media to another? Right? It happens all the time. Well, we could make use of something called a media converter. And look at this one I have going on here. This one converts between copper, that's an RJ45 jack right there, and fiber. That's a fiber SC connector right there. And we'll talk more about that in the next lecture. But in my server room, it's very possible I have to bridge between a fiber network and a copper one. And I can do it with a device like this. No discussion of Ethernet, especially over copper, is complete without talking about PoE, Power over Ethernet. This standard allows us to send electrical current to power devices over their Ethernet cables. Most common use for this, IP phones. right? Internet Protocol telephones. You may have seen them. They're Cisco devices or Anterasys or whatever. Cisco's are very common. And it sits on a desk, looks like a telephone, but it's really a node on a network. And it's using VoIP, voice over IP. Well, that device needs power, right? It's got a NIC in the back of it. It's got a little display screen, all that. Two different ways I can power it. It comes with a little power brick. I could stick in the back of it and plug it into the wall, and then just plug a regular Ethernet cable into the back of it, and there I go. What if I need my phone in a place where I don't have a power outlet? Like maybe in a factory floor somewhere, right along the assembly line, something like that. Happens all the time. But I still need a phone there. I need to call the line foreman or whatever. These VoIP phones are also PoE compliant in most cases, which means that they can get their power from their network cable. A couple different ways of doing that. I can have a PoE switch. And these are higher end switches, and they're along the same lines as like a Cisco 3750 switch or whatever. A lot of times they're called 3750 PoE, whatnot, and they cost a little bit more. And the reason they cost a bit more is because they're capable of providing this power over Ethernet. Alternatively, if I can't afford one of those switches, but I still need a PoE device somewhere, I could use one of these. They're called PoE adapters or PoE injectors, right? So that's somewhere maybe in my server room near my switch. I've got a regular network cable coming out of my regular switch sitting over here. It goes into the back of one of these bad boys. Cable from here, a plug, plugs it into the wall, so it gets its electrical current. And then out the other end is a PoE signal. So I got a cable right here that's carrying electrical signal all the way to the far end. You're not going to use these everywhere, but they're like any other tool. They have some very specific and very useful uses. And that wraps up the first half of our lecture over network cabling. When we come back, we're going to go in and take a look at the other big network cable, fiber optic, and we're going to look at some troubleshooting methods. I'll see you in the next lecture.